I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for these students. Pray that be with us today. Help us to, again, Lord, glorify you in what we do. In your name I pray, Lord Jesus. Amen. So let me just remind you our general program of study at the moment. We're basically, our goal at the moment is to find a particular solution to solve L of y equals 2. Just a second here. Which letter am I choosing today? I usually either use an F or a G there. I'm using F today. All right. So if F was equal to 0, this L, right? L of y is, what's my notation for today? Come on. Where'd you go? I have to check myself on this because I use different numbering sometimes. So I'm starting with a naught on the nth derivative all the way to a n on the thing. So a naught, the nth derivative, a1, the n minus 1th derivative, a1, an minus 1, y prime, plus any. So this L, right, is an nth order smooth differential operator, and we're trying to find some function that when we plug it in, it pops back out this other given function f, which has the interpretation of like force or something in physical problems, the so-called forcing function. We have tools to solve L of y equals to 0 when all those coefficients are constants, right? We write down the characteristic equation, we factor it. Of course, that corresponds to an operator factorization, as we talked about. And then we have this method of annihilators, right? So, comment, just a reminder, if a naught, a1, an are real numbers, and f is a solution to AF equals to 0, where A is also, let me just use words, a constant coefficient differential operator, if that makes sense to you guys. If I wanted to use kind of more formal lingo, I could say something like A is an element of the polynomial with real coefficients in the differentiation operator. This is math speak for that. Anyway, the point is if that's the case, then you can calculate, right? You can say, well, then ALY is equal to AF, right? But AF is 0, and then this is just a big constant coefficient, right? ODE. And as we discussed last time, we can pick out the form of the particular solution from that, right? That's what we did last time. We did examples of that last time. But then Luke brought up the question, well, what if f was 1 over x? Right, what would we do in that case? And I said, well, we can't do this in that case because 1 over x is not the solution for a constant coefficient ODE, right? There's no annihilator that's formed as a polynomial in the differentiation operator. So we need something else. And so that's where the next method enters in, which is called variation of parameters. So what I'm going to do for you guys is I'm going to derive it in the simple case, in an n equals 2 case, and then I'll talk to you about how we do it in the nth order case a second, all right? So I think the n equals 2 case is a little bit easier to follow. So I'm going to put away all this stuff. I'll leave that up here. So what we're going to do is we're going to specialize. we're going to focus in here on a slightly more mundane goal, which is to find the particular solution of, let's say, ay prime prime plus by prime plus cy equals to f. Okay, a little bit more manageable. And as I was talking to you guys about before class, the lion's share of physical applications fit into this context. RLC circuits, spring mass problems. I mean, honestly, if you really want to talk about physics, we should spend much more time talking about systems of differential equations in here. Because most problems involve not one spring, but several springs. And usually, see, you don't know how to solve that problem that you had on that quiz. If you just take one of those nodes and you just give it a little tug, then it's vibrating back and forth. And then you've got both of those springs going back and forth and the rods are moving. Like, that's next semester. That's dynamics. You're in statics, right? So, fine. Fair enough. But that would be a system of second-order differential equations you have to solve. And those can be solved. All right. So this problem. So what we're going to do, and I'm not assuming that A, B, and C are constants, okay? Here, A, B, C could be functions. And let's see, what independent variable do you want me to use, guys? Let's use x. We could use t, but I'll use x for the moment, all right? So what we're going to do is we're going to suppose that we at least already have solved the homogeneous problem, all right? So we begin by assuming we have a fundamental solution set. Assume that y1, y2 is fundamental solution set. So what's that mean? That means that y1 and y2 are linearly independent, right? In other words, they have a non-vanishing Wronskian, right? They can't be, one can't be written as a multiple of the other, all right? Also, that their fundamental solution set means that we have ay1 prime prime plus by1 prime plus cy1 equals to 0, and ay2 prime prime plus by2 prime plus cy2 equals to 0. Why is that? Because they are solutions to the homogeneous problem, right? Those are not solutions to the differential equation that we're studying, though, are they? You mean a solution's not a solution? Yes, well, we have to be careful, right? We have to be precise. These are homogeneous solutions. They're not solutions to the given, let me call that equation star. They're solutions to a corresponding differential equation where f has been set to 0. Right. All right, so method of annihilators out in our consideration today, so we need to do something else. And here's the guess that we do now. So we've seen that the fundamentals, the homogeneous solution, what's the general homogeneous solution look like? So if I'm solving, ay prime prime plus by prime plus cy equals to 0, we use what? We use y equals to like c1y1 plus c2y2. That's my general solution to the homogeneous problem, right? So what's a natural thing to try? I mean, I don't know how natural it is. It's just we're going to try it and see where it takes us, okay? I'm not sure this is... I'm not entirely convinced by what I'm saying either. I'm just telling you, as a matter of tradition, we try y equals to... Maybe that's not the greatest answer. This lecture could be improved. Y equals to v1 y1 plus v2 y2. Now here, where these v1 and v2 are undetermined functions of x, or that's the whole method. It's called variation of parameters, all right? These are the parameters which we're varying, v1 and v2. All right. Okay, so once you make this leap, I mean, once you start down this path, you make this guess, what do? Well, you plug it into the differential equation, see what happens, right? So let's do that. Before we can do that, of course, we need to differentiate, right? And so we've got y prime is v1, let's see here, v1 prime y1 plus v1 y1 prime plus, let's see here, v2 prime y2 plus v2 y2 prime. Let me just reorganize that just a little bit here. So that gives me v1 prime y1 plus v2 prime y2 plus, I gathered the derivative in v terms, v1 y1 prime plus v2 y2 prime. So, you know, let's see here, how can I say this? We're going to make this 0. So suppose this is 0. So that's going to give us this equation, v1 prime y1 plus v2 prime y2 equals to 0. All right. Now, the justification for that supposition, you have to wait a couple minutes for, all right? If you want a reason right now, I think the book says something along the lines of, do this so that you don't have a higher derivative condition on the parameters, right? Like if I don't do this, when I plug it into y prime prime, I'm going to have like second derivatives in v, and that's just as bad as the original problem. So how does it gain us anything unless we suppose this thing is 0? Again, I'm not entirely convinced, but whatever. So y prime prime. So we differentiate, what do we get? This is 0, so we can ignore that. Product rule over here, we get ourselves a v1 prime y1 prime plus v1 y1 prime prime plus v2 prime y2 prime plus v2 y2 prime prime. All right, and I probably should let me put up some p on this, because I'm just emphasize, I'm thinking of a particular, I'm trying to find a particular solution. Yeah, that's not, I mean, I don't know, it just makes me feel better about my life if I do that, but it's certainly not logically necessary. Excuse me. That will happen. And now what? Now we plug the particular solution into star, right? So plug the particular solution into star, what happens? That gives us A, this stuff, right? Plus B times yp prime, which was just v1 y1 prime plus v2 y2 prime, right? And then C times y, which is what? Y is just v1 y1 plus v2 y2, right? All of that is equal to F. Are you over far enough, Luke? Because I've written on the other board a little bit. Okay. So now you got to just kind of look at some stuff here. Like, notice some things common. So I'm going to collect this term right? I'm going to collect this term. I'm going to collect this term all together to give me, I'm going to pull the v1 out front. That's v1 times a y1 prime prime plus b y2 prime prime, y1 prime, oh no, plus c, feel a cough coming on. And then I'm going to deny the cough. Haha. All right, this one, this one, this one. So plus a factor of the v2 out there, v2 a2 prime prime plus by2 prime plus cy2, right? And then everything else is what? What's left over here? You just have these two terms, right? This guy, and of course the other side is f. So plus a, I'm going to, well, let me just say the stuff in red equals to f, all right? So what happens, what's this? What's that? What did we assume at the beginning? y1 and y2 are solutions to the homogeneous problem, right? So those terms are 0. 0, 0. And so you're just left with the red stuff equals to f. But it's better if we divide by a. All right? And what am I assuming about a? It's a function, right? Yeah, it's a non-zero function. So we've got y1 prime, v1 prime, plus y2 prime, v2 prime is equal to f over a. We call that 2. We call this equation up here 1. All right. So what have we got? We got two equations. And what are the unknowns? Oh, goodness gracious. Pleasant. Let me write them up here. Equations 1 and 2 are linear in the derivatives of v1 and v2. So let me write them out here. We got v1 prime y1 plus v2 prime y2. And here we have, I'm sorry, I should, oh, it's not how I want to write it. y1 v1 prime plus y2 v2 prime equals to 0. And down here we have y1 prime v1 prime plus y2 prime v2 prime equals to 0. So I can rewrite this as a matrix equation. y1, y2, y1 prime, y2 prime, multiplying the vector v1 prime, v2 prime equals to, and this was not 0, what was that? That was a typo. What's that? That's f over a, right? What's this? Yes, that's the Wronskian matrix. Now the Wronskian's the determinant of that, but this is the Wronskian matrix, which is invertible, right? It's an invertible matrix. Do you guys know how to invert a 2 by 2 matrix? If I have A, B, C, D, and I want to write the inverse of it, what's the formula? Yeah, AD minus BC. You flip the diagonals. minuses on the off diagonals, right? So basically I can look at this as the equation AV prime equals to, let's say, F vector for the moment. Fine, put some vectors in. And so if I want to solve that by multiplication by inverse, I just say A inverse AV vector equals to A inverse times the F vector. What's A times A inverse? Well, that's the identity, right? So this just gives me V prime equals to A inverse times F. I mean, that's the calculation I want to do here. I want to solve for V prime. So if I take this excuse me, if I take the matrix equation up here, this guy, right? I multiply both sides by the inverse of the Wronskian matrix. So what's the inverse of the Wronskian matrix? So what is that? I mean, the determinant, right? So this is exactly the Wronskian itself in the denominator, right? And then this, of course, if you y2 prime y1 minus y2 minus y1 prime. So multiply both sides by that. That gives us the following. It gives us that v1 prime v2 prime is equal to 1 over the Wronskian, which is y1 y2 prime minus y2 y1 prime, times this matrix, y2 prime minus y2 minus y1 prime y1. So I'm going to multiply that by the vector 0 and f over a. Now, guys, if you're not comfortable with this like 2x2 matrix vector stuff I'm doing, I'm sorry about that, but it's really, I think, the most organized way to do it. The other way you could do it, of course, is it's two equations and two unknowns. You could solve and substitute if you're more comfortable with that, you know. But I think it's a good thing to have more experience with manipulation at the level of vectors, you know. So that's why I'm doing it that way. I'm doing it the way I think is most edifying for your mathematical education. Maybe it's not the way that's most understandable to you at your current juncture. Okay, anyway, so y2, y1 prime, and then when you multiply, how do we multiply this, right? You guys got to look at me. So we do this times that, right? That gives me 0 y2 prime minus y2 f over a, right? Then I do this times that to get the lower component. That gives me 0 times y1 prime, and then plus y1 f over a. So this is multiplication by that thing outside, right? So I mean, I can rewrite that. Well, I don't want to rewrite it. I mean, let me just go ahead and what does it say? It gives us two equations. If you don't mind, I'm going to write them back over. Yeah. I don't think we need all this now. So I'm going to. We don't need the derivation of the derivatives anymore. We can get rid of that. Excuse me. Don't worry, I will not write out the nth order derivation. I should try to go somewhat slow through this. So dv1 dx equals to what? That's this, dv1 dx. It equals to the first component over here, which is what? It's minus y2 f over a, right? I'll put the a down here, and then I'll multiply by the Wronskian. y1 y2 prime minus y2 y1 prime. Did I get that right? Yeah, okay. And then dv2 dx is equal to y1f over a y1 y2 prime minus y2 y1 prime, right? There are different schools of thought on how you should teach this material. well, how you should ask students to do these problems. My personal opinion is that you derive these formulas once and then you use them. Because while I love linear algebra, I don't see much the point in going through the deriving of this system, 2 equations and 2 unknowns, every time you do this. So I feel like you do this once carefully and then you use it. Now I might ask you to work out some of this on the test or something. I suppose that's possible. But I also would allow you to use these formulas to solve problems without deriving them, all right? Yeah. So you integrate. And there we go. And then, so, indeed, yp equals to v1y1 plus v2y2 with v1 and v2 as above serves to solve, ay prime prime plus by prime plus cy equals to f. We should pause to appreciate something. A does not have to be a constant. B does not have to be a constant. C does not have to be a constant. We nowhere used that A, B, and C were constants in this. The only thing I needed was that A was identically non-zero, because I divided by A, right? And what's standing in the way of doing this is just that those integrals, right? So not only will it treat the 1 over x function that Luke brought up, it'll anything you can integrate pretty much, right? So this method is stupidly general. It's very general. Let me show you an example, if that's okay. Yeah?
Just wondering, we are now at a place where you could explain why you chose to set v1 prime y1 v2 prime y2 v0.
Right, because that becomes part of this equation, which we know we can solve. It's ultimately based on the fact that we know the Wronskian's invertible, and the setting, if we decide we're going to search for equation, so thinking backwards, if you can solve for v1 prime and v2 prime equals to functions of involving the a, the b, the c, y1, y2, and its derivatives, all of which are given. If you can solve for dv1 dx and dv2 dx equal to stuff, then you can integrate it, right? So also we happen to know that, so that means you're thinking of v1 prime and v2 prime as variables, right? So with that in mind, you know that you also have this Wronskian to play with because you have linear independence of the functions, right? So that first condition is this equation, right? And that's part of a package deal. Well, if you have another equation that involves y1 prime and y2 prime, you can solve that because that's the 2 equations and 2 unknowns that comes from the Wronskian matrix. I don't find this to be entirely convincing either. But nevertheless, it does work. Again, I'm not entirely... I think this lecture could be improved. But I'm not sure how to improve it right off. Okay, so let me show you how it works, though. You can enter into adulthood saying, I want to find a mate. I want to have certain physical characteristics and certain personality characteristics. And your friends might say, well, that's impossible. That it's not conceivable that such a woman does not exist, right? But the thing is, once you find the woman and you marry her, you've proved that she's a solution, right? So it works. And it's the same thing here. However implausible it was to make this condition on our search for a solution, we have shown through these calculations that it works. Admittedly, it's not a derivation, but it is a solution. Derivation's a higher calling. Excuse me. Let's solve a problem. Example. I think I could get rid of this. Suppose we want to solve y prime prime plus y equals 2. Oh, fine, we'll do Luke's 1 over x. I regret this. I don't know if we can actually solve this. We may have to be content with an integral solution, all right? But, so what's our fundamental solution set? First of all, to make variation parameters work, you have to find the input, right? You have to find the fundamental solution set. How do we do that? Let's see, I got myself lambda squared plus 1 equals to 0. If you ask me why it's not equal to 1 over x, I kill you. Let's see here, lambda is equal to plus or minus I. Sorry, there used to be a professor where I was an undergraduate who he would tell the students, like, if you come up into the hallway and if I ask you, after my class is done, if I ask you what's the fundamental theory of calculus, and if you don't tell me, I'll kill you. He's very famous for saying this, but anyway, I don't quite go that far. But so this tells me that y1 is cosine, and y2 is sine. Now, it doesn't matter which one you call y1 and which one you call y2, but you make a choice and you stick with it, all right? You can't relabel them mid-problem, otherwise then you'll get into trouble. All right, so we're doing variation parameters. So it's in our best interest to calculate the Wronskian now. You don't want to calculate the Wronskian 2 times as you're applying these formulas. All right? I think these are equation 10 or something like that in the book. But I'm thinking of a different edition of the book, so I'm not sure. It may be equation 10. I think these might be equation 9. I don't have my book in front of me. You guys? Oh, good. That's fine. It doesn't matter. Oh, yeah, all right, fine. I'll take a second. I guess something useful can come of this. I'll tell you which section we're in. 4.6. Yeah, this is equation 10 is the integration one. Equation 9 in blue on page 195 is the scalar version of my blue equation. That blue matrix equation I have is entirely equivalent to the set of 2 equations he has in the blue there on page 195. All right. So anyway, so my point is to use equation 10 properly, calculate the Wronskian first. What is the Wronskian here? y1, y2 prime minus y2, y1 prime, which is what? Cosine of x times the derivative of sine, which is what? Cosine of x minus y2 sine of x. What's the derivative of cosine x? Derivative of cosine? Minus sine, right? Hey! Awesome. This is 1. Because you get yourself sine squared plus cosine squared, right? So, hence, by equation 10, we built this machine. Let's use it, right? V1 we can construct as the integral. I guess I should recognize here a is equal to 1, right? F is equal to what? 1 over x, right? Okay, so. Oh, yeah, now we have to face the music. So minus, what is it? Now, V1 has y2 in it, all right? So minus sine of x. There you go. I mean, any way you slice it, Luke's function is still unpleasant. At least for this problem, it's unpleasant. I mean, I can calculate those integrals with power series methods. Certainly you have trouble where x equals to 0. But that's not terribly surprising because the force is undefined at x equal to 0, right? So that's an integral solution then. Y equals to, say, c1 cosine x plus c2 sine x plus cosine of x integral. I put a minus here, minus cosine of x sine x over x dx plus sine x integral of cosine of x dx over x. This is what's known as an integral solution to the problem. Of course, it's more satisfying when we can actually do the integration, right? I mean, I could do them if you want to watch me do it at the level of power series, but let's just leave it there for now. We'll get to power series before you know it, don't worry. You're like, yeah, I miss power series. I want to get back to them. Sweet. Awesome. Hey, wait a minute. Austin? Just realized. He's still engrossed in my notes. I only hope he watches this later. Let's see here. Okay, so, all right. Of course, all right. Another problem. I'll work another example here, which will be a little bit more fun. Same underlying differential equation, different force. This seems scary, right? I mean, secant, ugh, right? Okay, by the same song and dance again. Y1 cosine, right? Y2 sine. And we know the Wronskian's 1. We can calculate V1, the integral minus the secant of x times y2, which is sine x. All right. So V1 is minus the integral. And what is secant? So that's sine x dx over cosine x. Well, that ain't bad. See, that's minus the integral of that's just the integral of d cosine x over cosine x, also known as log of the absolute value of cosine of x, plus a constant. Have you guys ever seen that notation before? This is a way of getting around writing u equals to cosine x. Du is minus sine x dx, of course, right? If you like, that's better. But this differential notation allows you to do u substitution without actually writing u. It's very slick. Now V2, V2, V2. You guys are going to like V2. V2 is the integral, let's see here. Oh, I erased my formula. But it was f v1 over the Wronskian dx. All right, so that's the integral of secant x cosine v1. Listen to me. y1. So that's secant x times cosine x dx. Okay. Because secant and cosine, it was the integral of dx is x. All right. So, therefore, y equals to c1 cosine x plus c2 sine x plus where was I? Yeah, cosine x, the natural log, the absolute value of cosine x, plus x sine x is your solution. Of course, the last two terms are the particular solution, and I just, included the homogeneous solution there. Again, referring to the theorem that we keep referencing about the general solution set being formed by a sum of the fundamental solutions and a particular solution, however you happen to find it.
Just a quick question. I
Sure.
wasn't seeing where on the second velocity, so you have cosine times the natural log cosine, and x times sine. What is the cosine sign?
So it all goes back to what we started with, which was that yp is y1 v1 plus y2 v2, or you could write the v1s first. I just wrote the. Okay, so here apparently I have written. So let's see, that's y1 v1, and then over here I wrote v2 y1. I mean y2 v2 y2 rather. I don't know. I just.
Oh, okay.
For aesthetic reasons, I like to write the x first, and I like to write the cosine first. But I mean, yeah. don't ask me to define the aesthetics. I just call it like I see it. All right. Now, it gets uglier. The integrals can get nasty, right? But now we have a method. A pretty clear-cut method for solving second-order non-homogeneous problems with this method. Now, you're like, well, only for constant coefficient ones, though, right? Because how do you find the fundamental solution set, right? How do you find the fundamental solution set for something that doesn't have constant coefficients? Like, are there any other cases which are known besides the constant coefficients to have? I mean, how do you find fundamental solution sets for problems that don't have constant coefficients, right? That's another question that we should ask. So there's two directions I can go down at this point. The one is to show you how this works for higher order differential equations. I'm going to project that at the end of the class. I'm just going to spend like 10 minutes running through it with you guys, showing you a couple of examples I worked out in the notes, maybe last 15 minutes, right? So for the next 15 minutes, I'm going to show you something called the Cauchy-Euler problem, which is another problem we can actually calculate the fundamental solution set for. So let me state the problem for you. So here's another problem we can solve. So I'll start out small, something like ax squared y prime prime plus bx y prime plus cy equals to 0. Now sometimes this is also written as ay prime prime plus b over x y prime plus c over x squared y equals to 0. Those are essentially the same problems. All right. For the moment being, we're going to assume that x is greater than 0. All right. This is what's known as a Cauchy-Euler problem, or sometimes equidimensional. Now, if you look at this, right, do you guys have any suggestions for me? Like, what would you make as a solution to this? You're looking for some function, right, that you can add it. So you have like, this differential equation is such that I can take this thing and I can add it to things which are formed from x times its derivative, right? And over here I have x squared times the second derivative. What kind of function? Whoa, weird. What kind of functions would have these in common? These terms. Yeah, here A, B. Oh, good question. Here now A, B, and C are constants. Yes. So, yeah, fine. So I would say that. Let me put some quotes around it. My A of the previous discussion is now ax squared. All right. The B of the previous discussion is in this case bx, right? And you can say that C is c is equal to c, all right? So what I'm trying to say is we're looking at, here's another problem with non-constant coefficients that I actually can show you how to solve. I'm putting quotes. This is from the previous arc of the class, right? So, but yes, this A, B, and C. If it helps you, I could, no, I don't know. I'm tempted to put bars on these, but I can't do it. You guys understand what I'm saying? Okay.
It's something nice using caution cinch in this case.
But if I have cosh here, then over here I'm going to have an x cinch. And over here I'm going to have an x squared cinch or cosh. How can those cancel? They can't cancel. Exponential won't work, right? Sine and cosine won't work. Because like, if you have a sine here, you have a cosine here times an x. Those can't cancel. What can work? How about this? How about a power function? Yeah, they're back. So, I mean, this is in some sense simpler, right? But that works because on the one hand, you have the rth power here, right? You differentiate, that takes you to r minus 1, but then you multiply by x, so you're back to power r. And here, you differentiate 2 times, you're down to the r minus 2 power, but then you multiply by x squared, so you're back up to x to the r. So these terms all produce the same sort of thing when we feed it this function. So we have hope that they cancel, right? So this is our guess. And there is a way to derive this from a rather clever substitution, all right? Or if you like, we could solve the one-dimensional version of this, you know. Derivations for another day. Anyway, so guess the solution's that. What's y prime then? Yeah, r is a constant, yeah. Y prime prime. So that's r minus 1, x to the r minus 2, right? So you feed these into the differential equation. What's this give us? A x squared r times r minus 1 x to the r minus 2 plus b x r x to the r minus 1 plus c x to the r equal to 0. So of course we can rewrite this as a r times r minus 1 plus br plus c parentheses x to the r equals to 0. So again, there's some kind of simple algebraic condition on this constant, which is dictated by the differential equation, right? So we can't make r can't just be chosen to be anything. It has to be something that forces this particular algebraic equation to be 0. It was more simple in the case we had constant coefficients, right? But this is basically what's playing the role of the characteristic equation here. So we need a times r times r minus 1 plus b times r plus c equals to 0. You could reasonably say that this is the characteristic equation for the Cauchy-Euler problem. The n equals 2, 1. I mean, there's also an nth order version of this. All right, let me try one. Hopefully I won't get us into trouble. Example. If I had x squared y prime prime plus 4xy prime plus 2y equals to 0, Let's find a fundamental solution set. Okay, so by this derivation, I'm going to look at r times r minus 1 plus 4 times r plus 2 equals to 0. That's my characteristic equation, which gives me what? That gives me r squared plus 3r plus 2, which is r plus 1 times r plus 2. So our characteristic values, we have r equals to minus 1, r equals to minus 2. And so there you go. Our solution, we get y1 equals to x to the minus 1, and y2 equals to x to the minus 2. I'm so very happy about this example. We have now found a home for Luke's 1 over x. Apparently, it is the part of the solution set to this differential equation. Who knew it? And what's the general solution then here? Y equals to c1. C1 over x plus c2 over x squared. There you go. It just so happens that that is the solution either for positive or negative x, but not 0. Right? In principle, you could have different choices of c1 and c2 on the left and to the right is 0 as a given solution to a problem. But anyway, so let's see here. I forget what section this is in the book. Steal your book again here. I have more to say. I mean, there are some obvious questions, right? What if r? I mean, r is that's a quadratic equation, right? What are the choices? You could have a complex coefficient, right? You could have a repeated root. What do we do in the repeated case or the complex case? I'd rather not talk to you about that right now. We don't have enough time, right? We need to derive. There's a wonderful result for the second order case. Where did he put that stupid thing? I was trying to find it the other day. I can't. Anyway, it's in here somewhere. I guess I could use the. This is actually a really important example because it's an example of a differential equation with what's known as a regular singular point. And let's see here. And that's like the start of a much larger discussion that we have in here later about something called the Frobenius method, which is, well, I think it's the most formidable calculation that we come across in this course, personally. All right, I can't find it. It's okay. It is in here. But yeah, there's a wonderful thing that when you find one solution to a second order problem, there's like a formula to create a second linearly independent solution by doing a certain integral over an integral. It's a weird formula, but we'll derive it maybe next time. So anyway, here's an example of something else we can find a fundamental solution set for and thus do variation of parameters on, is my point. So like here, now that we've found the fundamental solution set is 1 over x, 1 over 2, like this, right? We could try to do something like solve x squared y prime prime plus 4xy prime plus 2y equals to, whatever you want to put there. I want to put like x to the 6th because I feel like it's helpful. So if I was to try to solve this, I think I have a shot at actually solving that problem. What's the Wronskian here? So is it 1 over x, 1 over x squared. Derivative of this is minus 1 over x squared, right? Derivative of that is minus 2 over x cubed. So I get minus 2 over x to the 4th plus 1 over x to the 4th, right? So the Wronskian is just 1 over x to the 4th, excuse me, minus 1 over x to the 4th here. I'm letting y1 equals 1 over x, y2 equals 1 over x squared. My v1, again, integral of minus f y2 over the Wronskian. And here, that's the integral. I'm making f equal to x to the 6th. So I've got minus x to the 6th. My y2 was what? 1 over x squared, right? And my Wronskian was 1 over minus 1 over, what did I say? X to the 4th dx. Can we do this integral? Indeed, I think we can. That is integral of x to the 8th. Is that right? Yeah. So this is 1/9 x to the 9th. v2, integral of f y1 over w. No minus here for the reasons we explained earlier. And so that's the integral of, what we got here, y2, 1 over x to the 6th, 1 over x squared, over minus 1 over x to the 4th dx, which is the integral of what? Is that x to the 8th again? Cool, but minus x to the 8th this time, right? So we get minus 1 over 9 x to the 9. And so therefore, my general solution is c1 over x plus c2 over x squared. Oh, you guys, don't let me do that. You guys, come on. You gotta stop me. What was y1? X. Yeah. So this is 9. So we got a 10 here. Okay. So plus 1/9 x to the 9 times y1, which was 1 over x, right? So that's just x to the 8th. And then minus 1/10 v2 times y2, which is x to the 8th. This happens a lot, guys, with problems. You end up seeing that the v1 y1 term and the v2 y2 term are like actually just two parts of the same puzzle piece, and then they might be able to simplify. So sometimes if you do this method and you find an answer that doesn't match the back of the book, it could just be that there's some kind of like way to simplify these, you know? Let's see, if I put those both in 90ths, we got what? We got 10 minus 9. So what is that? 1/90th, that's 1/90th, is that right? I can't, okay, so. So that's my particular solution here. The point is, in order for you to do variation of parameters, right, you actually have to, well, let me start until I have my computer over there. It's so annoying. In order to do variation of parameters, you actually have to have a fundamental solution set, right? Now, there's two ways that that can happen. You can find it, right, or it can be given to you. So there's a kind of halfway point for these sorts of problems. The book might say, hey, here's a fundamental solution set for a problem.